Welcome to our session today. My name is Ali Raza Klagi. I'm the product manager for the material testing side at PROCEQ. Today I'm joined by my colleague Guido Tronka.
Hello everyone.
Which is our product manager for the concrete testing. We also have today with us Andre Naff, who's our head of global marketing, along with Serena Dorongs, which is our marketing specialist. They're working very hard in the background, making sure that the session is running smooth for us, coordinating everything. And as I said, if you have any technical difficulties, they are there to help you and help obviously resolve the issue that you may be facing. So on that note, let's begin our session. Just for your information, today's session is one of the two webinars that we're doing on resistivity. There's going to be another session on Thursday, which we focus mainly on corrosion analysis and dealing with more of a sort of a on-site existing construction sort of testing. Today we kind of focus a little bit more on the actual surface resistivity principle and the guidelines and standards that are available to us and why we do such testing, and we kind of also do a little bit of a comparison testing. So on that note, let's begin a session. Surface resistivity is now becoming one of the tools being utilized in the construction industry. And durability of the concrete being a big concern has imposed certain sort of pressure on the concrete manufacturers towards certain requirements for performance-based specification. And what we mean by that is that there has been standards and guidelines developed to allow the construction companies to perhaps modify and come out with certain mixes of concrete to suit the environment that concrete needs to go to. Now, durability of the concrete is not necessarily related to its compressive strength, but traditionally, in order to sometimes define the durability of the concrete, what we used to is to do, for example, cube or cylinder crush tests to find this compressive strength. Traditionally, the methods being used and utilized for durability could be fairly labor intensive. They take a lot of time, and when you compare it, for example, to the resistivity, electrical resistivity test, you see a significant decrease in the time and the costs involved with the testing. And when you take all of these benefits into account, you'll see that electrical resistivity testing of concrete could be a very versatile tool that could complement your productivity and equally profitability at the same time. These are the things we're going to kind of cover today. Just wanted to kind of give you a bit of an overview. We're going to use some examples. We're going to refer to some case studies that we've looked at. A lot of them are actually from the North American region. Let me kind of break it down for you in examples. As I said, the Q&A box is there for you. So if you have any questions during the session, please go ahead and send it to us. We'll receive it. We'll look at it. If it's relevant to that particular portion of the presentation, we had a session this morning as well, we will deal with it there and then. If not, every one of your questions we will look into thoroughly and we try to answer them for you. And if there's any supporting documents required, we will send it to you separately. By all means, you can always contact us at our dedicated webinar email as well, which is webinar@proceq.com. So let's begin our session today. One thing we'd like to do, about approximately 5 minutes or so, let's say, we're going to talk about this sort of a theoretical side of electrical resistivity test principle and give you some sort of background to it, how it began and where we kind of stand with it at the moment. So electrical resistivity is a fairly simple test procedure. But if it's utilized and used correctly, it could be a very powerful tool for concrete testing. Corrosion of the reinforcing steel is generally the main cause of concrete deterioration over time. And the expectation from the concrete is that over the life cycle of the construction to provide both physical and chemical protection to the reinforced steel. One of the things we were talking yesterday, Guido came out with some good examples for the alkalinity of the cement content of the concrete and how it protects the chemical protection that is required in this case. It will definitely break it down for us a little bit later on. Now, electrical resistivity is directly related to the ability of concrete to provide this protection or resist the access of the aggressive agents to the steel that could potentially lead into the corrosion. And this is practically what we can utilize and use electrical resistivity for, to kind of identify the problems that we could potentially facing with. We will have two scenarios here. The case one for us would be new structures, so where we're kind of dealing with durability. Guido will kind of break it down for us a little bit further, actually break down each example. And the second scenario that we could potentially be dealing with is the existing structure, where we're potentially looking for corrosion and the likelihood of it is happening. We've got some examples here for you, as you can see on the picture. But potentially what we're looking for in your new existing structure is you identify and the potential or the likelihood of having corrosion. You kind of come out with the repair and the maintenance program, which could perhaps be systematic. You implement the repair work that needs to be done, and then you go back and perhaps use your resistivity tools to verify the effectiveness of the repair that has been implemented. So you've done the repair, you want to know like all the work that has been done, it's been done correctly, and so that it's actually doing what it's supposed to do. Let's see what Guido, give us some examples of these sort of scenarios, Guido. Let's kind of break it down and get it a little bit more.
That goes back when we, together with Ali, were trying to find something in common that main applications could have. And so it could have been, lab testing versus on-site testing. But going back to some of my experience and most of our experience of my colleagues, whoever is involved in the testing, well, it depends on who's paid by. So typical case for sure is they're building a brand new house, next block, and these guys have lots of things to check. There's going to be a lab, probably. There's going to be for sure a supervisor checking that certain properties are met by the contractor. So in this sense, resistivity is part of the testing that is being done on a new structure in order to assess the durability. And we'll go into the details later. This is the scenario which involves mainly lab testing on cylinders, but not only, but always has to do with a new project with some defined specification. This is the American approach, basically. The U.S. are the leaders, are the ones that set the trend for checking for durability on new structures. Something different is the checking for corrosion of an existing structure. You might be involved by the structure manager providing all the history, all the details, or you might have just to provide all the info on a totally unknown structure. This is the second kind of scenario, mainly dealing with the on-site testing, and which will be totally covered in Thursday webinar. So all the details about half cell potential and finding corrosion spots, those will be the goals of next webinar. While today we're basically checking a new structure.
Fantastic. And on that basis, so as we try to identify the type of work that we need to do, the type of structure that we're dealing with, when we move on, for example, we need to obviously consider and find out the factors that directly affect the electrical properties of the concrete. The first thing that comes into mind is obviously the water content. Moisture is the key here. Later on in the presentation, we will go back and keep referring to the water content. On the other side, as you can see on the pictures that we got here for you, salinity of the pore solution is a big factor. Porosity and finally the interconnection between the pores dictates the electrical resistivity or electrical properties of the concrete that we're kind of dealing with, potentially affects its electrical resistivity. So these are the things we need to really consider. And there has been obviously case studies and applications have been covered and research have been carried out with certain institutes and universities. In this particular University of Purdue in US, they have some great papers that for this presentation we actually had looked into and referred to. And personally, I was lucky enough to visit University of Purdue earlier this year with one of my colleagues in Chicago and have a meeting with Professor Weiss to discuss the resistivity application in US. Now, if we were to kind of break down the electrical resistivity, we could say, let's say, we can put it in two categories, and then say this is how the test could be carried out. We've got the surface resistivity, which the current is applied to the outer probes, and then the potentiality between the inner probes. And then the resistivity is calculated based on the spacing of these probes. And on the other side, we've got the bulk resistivity, as you can see in this picture over here, where we apply the current to the entire specimens and look at the resistivity of the entire, sort of in this case, cylinder. The only difference in these two cases are that you just set the device to the appropriate mode dealing with that particular geometry. And these modern instruments nowadays, they take care of that for you. So you just have to use the software to adjust it to the functionality that you're doing the testing, i.e. whether bulk or surface. And the rest of it is done for you automatically. Now, this is the section that's hopefully what we've covered here. We give you a little bit of a background about the surface resistivity, where it's implemented, what are the factors affecting it, where it could be, in general term, implemented and utilized. And now we're going to go into sort of a main portion of the presentation, which we're going to kind of use resistivity measurements as a quality inspection for new structures. Again, during this portion, I'm sure you will have questions. While the questions are fresh and you have fire away, send them to us. If relevant at that particular section, we will try to cover them there and then. If not, we will get back to you at the end of the presentation and cover it for you. Now, earlier on in the presentation, we covered that in recent years, because of the need and the demand of the industry, now durability is kind of becoming a performance-based specification, where the construction industry follows a certain guidelines and the standard to produce a particular mix and going through particular curing processes to meet the demand or the need of the environment that the country is to go to. Based on that, they have to develop and come out with what they call exposure classes, where they kind of define certain environmental conditions that this country is going to be utilized and used in. And there are other factors contributing to this as well, which are clearly identified, like the cover of the concrete. We covered it earlier. Concrete cover is what it provides that protection to the reinforcing the steel, preventing it from getting corroded. And obviously the concrete strength itself, that's defined in these exposure classes. One of the things that we picked a couple of examples for you. First one is from DIN, which is a German standard, Deutschland Institute of Norm. We also have a British standard for you. As you can see here, if you look at the top of the graph, we've got one of the sort of almost like you can say the best, but more of an ideal scenario. And right at the bottom, you got like one of the probably harshest sort of scenario. Guido, yesterday we were talking about these conditions again. We were having a pretty casual discussion about it. I was thinking, so give me an example of like what would be the harshest environment and why. And you had an example of shore for me,
sure,
and the seawater. And I think it was a great time to kind of share the same sort of story here.
Of course. Well, what this standard what is mentioned later, the PS, is more or less the same, apart some numerical values. But we have increasing aggressiveness of the environment with regard going down in that column. And so while it's normal to consider a dry concrete a safe concrete, it is normal to consider that, hey, if it's in the water and I'm fearing rust, that is dangerous. Well, that's slightly more complicated in that corrosion, without going into too many details, but corrosion, in order to progress, needs at least moisture to carry the electricity and oxygen, which is a fundamental reaction.
So you get a chemical reaction. Obviously.
Absolutely. So a totally submerged environment will satisfy the need for moisture, but will totally prevent oxygen to go in. So that will be the moisture. But so the same concept might explain why we find right at the bottom of the list the tidal splash or spray zones, where alternate in cyclic you can find the moisture you need to go on with corrosion, but that will stop and then allow oxygen to go in. So that is the worst scenario in this case. And just qualitatively speaking, we just have a table stating that the worse the scenario, the thicker the cover, meaning you need more protection, and the stronger the concrete, because yes, concrete strength, it is somehow a measure of the degree of protection, but it is not the ultimate measurement for durability. As it is today, people still pay for concrete strength. Designer put down specification, and contractors do provide and test strength. But how about how can we be sure of what will be the structure like in 50 years? And so this concept of finding the best parameter to assess durability and to use that as specification and to test for that and pay for that and have that delivered on site was what moved the first investigations of basically the Federal Department of Transportation in the States, which will probably be presented somehow.
And based on that, we also got other standards now. So we talked about the British standard, which has a similar sort of guidelines, let's say, don't they? I mean, we looked at these yesterday, and we couldn't say they were the same, but they're very much identical in a way. The recommendations are very similar, wouldn't you say that?
Absolutely. You may find some numerical differences, but the concept remains the same. I mean, the aggressiveness of the environment is assessed according to the same criteria, and the tougher the environment, the stronger and the concrete has to be.
Absolutely. Brilliant. Okay, now, the first or the initial approach when it comes to assessing durability is basically to look at its sufficiency, like we again said earlier, or its optimal amount of protection that is capable to provide to the steel over the life expectancy of the lifetime of the concrete and the construction. Initially, the guidelines, the standards, that again, so we talked about the importance of the standards and why some of these were developed. The guidelines and the standards that were used, the approach was to penetrate some sort of an aggressive agent, which in this case was like chloride ions, onto the concrete sample that are exposed to these sort of accelerated weathering conditions. And then almost defined some sort of a correlation between what they do in the lab and then taking that and doing a comparison to the existing or construction, for example. And you've got your several AASHTO standards and the ASTM standard. Again, we were discussing this yesterday together with Guido. We're kind of going on about like why these standards were initially developed. Is what are the importance of these let's say steps that had to be followed, and what was the importance of these procedures to be kind of having that sort of guidelines and then generalize the steps so they kind of almost like marry each other, so you could take the information and do like an A/B, like apple to apple comparison in a way, isn't it?
Absolutely. Well, this was actually the first answer to the question that arose before. Mm-hmm. If concrete is not the parameter that I want to measure, then what? Okay, these are basically the fundamental three way of testing, which are all based to the measure of the ease of migration of specific ion, basically chloride ions, by mean of laboratory testing under accelerated weathered samples. Mm-hmm. And they're all electrical testing. So that was the first answer, and that provides a measure and then an estimate of the depth of penetration in a number of years. And that has become the sort of a base fundamental method to analyze the durability. It is just like crashing a core for measuring concrete stress. And whatever we're doing now, even when it comes to electrical resistivity tests, we correlate that to the RCP basically, right? And that's what had to be done in order to establish the measurement. Right. So I think this is what is following. Absolutely. So based on this, so the correlation has to be done. So there were some earlier studies carried out. And in earlier studies, what we kind of saw that there's an imperial correlation between the standard methods, RCP, rapid chloride permeability test, and the resistivity of water-saturated concrete. Then surface resistivity, as it was introduced, as the AASHTO standard, it kind of indicated electrical resistivity test for permeability use because when they started to comparing these test methods, finding the correlation between them, the electrical resistivity test is far less labor intensive, and the test could be done really, really quickly. Original case study in the test was done with RM Mark II, which is a CNS Farnell instrument, and CNS was then later on brought out by PROCEQ, and which later on we will cover how we kind of got into this sort of a latest Resipod instrument. As I explained before, when you compare the RCP test to the electrical, so surface resistivity test, for example, you find that the RCP test could take as much as 30 days for it to be completed because it has to be done some period of time, or you can literally do an electrical resistivity test in approximately 10 minutes. And the advantage of having of doing electrical resistivity is you can use the same sample to be passed on for other test methods. If you're in a lab environment, I mean, what you do in a concrete lab, you crush concrete. So that sample could be passed on to that department. It could be crushed, and you can look at analyzers, compressors,
strength, for example?
I mean, in terms of preparation, it's not that preparing a cylinder has no cost whatsoever, but keep in mind that you prepare the sample the same exact way that you would do for the fundamental compressive strength testing. Once you do that, then we'll see it live. In a matter of minutes, you add the information about durability.
Absolutely. And then you can, by doing several different tests on the same sample, you can create additional correlation, can't you? Which could be, especially for the institutes and research center, that's a bonus, because you can create like other stuff that could be fairly useful and kind of supplement your studies. As highlighted earlier, the RM Mark II by CNS became the sort of almost like the foundation or the idea to develop the RESA card. And then PROCEQ, we agreed to develop the new instrument for the Florida Department of Transportation. I've got a little graph here for you. It's a collection of several different research and case studies, and you can see right from the get-go that there is a very nice correlation between the RCP and the resistivity test. And based on that, there was a table developed, which Guido is going to break it down for us again. This case study, some of it belongs to, again, University of Purdue in the US, and this particular one was from the 2003 paper that we kind of looked at. So I'd say to you, just break that down for us.
Absolutely.
Like maybe a minute or so.
Sure. It's just very clear just from the graph that there is a correlation between what is accepted as durability parameter, direct one, the rapid chloride penetration test, and this newfound surface resistivity. The correlation is not linear in itself, mainly because of temperature effect that affect the RCP when higher quantity, higher electricity flow actually heats up the solution.
Sure.
But apart from that, those studies led us to that table on the left, which can allow us to classify the performance in terms of penetration, chloride penetration, from high to negligible, not only by the direct testing, but we can assume now that, for example, a cylinder which will display a surface resistivity below 5 kiloohm centimeter can be treated and regarded just as a sample where a high charge more than 4,000 coulomb will pass, and so that is highly at risk. And with this knowledge now, I think that was what made available the NDT instead of the direct testing. Huge money to be saved.
Great. And talking about the NDT side of things, as these case studies and research, they came to light, they did additional testing, not just on the sort of technical side of things, but on the physical, mathematical side of things. But they started looking at the cost benefits that this particular test principle could impose. Based on the sort of data that we found from Louisiana Department of Transportation, they estimated that in the first year it'd be saving over $100,000, and the contractors would end up saving something in the excess of $1.5 million just in the quality control side of things. So that's significant. It kind of reflects, you also, I'm sure by this stage, looking at the time and the labor intensive side of things, when you look at things and you compare it to the resistivity, you've had an idea, but these numbers are fairly good, and we know it does make a huge difference right from the get-go. And based on such case studies, all these data get it together, the ASTER standard was created and it kind of became, in a way, the industry standard for resistivity tests, especially in the North America region. Now that we know about sort of a history of resistivity, in a way, where it began, what we use it for, what is its relation to other test principles, I think we should start looking at that, get into the lab. So first thing we talk about, you looked at the standards as well, we said there are certain things we need to get. So before doing any test, we need to consider the main factors that affect that test. One of the main factors contributing to or affecting the electrical resistivity test is the temperature of the concrete. And these are specified in the standards that we talked about earlier. The curing condition of the concrete, again, is a contributing factor. Again, this is specified in the standard. Lastly, the geometry of the sample and the concrete that we're dealing with. There are different sizes of specimens. Some regions use cylinders, some use cubes, so you need to take this into consideration. Later on, we kind of introduce different accessories in the kits to suit different type of geometries as well, so that's not a problem. And we again cover the differences between them. While we're on the geometry side of things, the industry standard for resistivity was 15 millimeter spacing. But as the ASTER standard was developed, and due to the size of the cylinders in the US, to avoid being too close to the edges of these cylinders, which you'll see over here as well, then the 38 millimeter resistivity probe spacing was introduced for the Resipod. And as we're kind of talking about all these probe spacing, you also have the option of having the geometric kit, which allows you to have custom spacing. The main reason for that is that when you're dealing with aggregate size larger than 1.5 inch, 38 millimeters, you need to define your own spacing. And the beauty of this particular instrument, our Resipod, is that you'll be able to set the geometries with the software and go ahead and then do the testing, which makes things really, really easy. Gita, just give us some examples of like how we end up, which applications, which areas we kind of be looking at these geometric kits, and where we should be able to, where we end up using them more. Let's put it in that way.
Well, the basic concept is that the spacing is as a compromise between having a larger spacing than the aggregate size. So, well, in principle, we could have huge spacing always and be happy with that. But when we test on cores, we don't want our probes to be too close to the side of the core because, you know, the model is still on an infinite length and it has to be modified for a shorter distance. So the first standard for lab testing took into consideration that for a standard 20 centimeter long cylinder and a spacing broader than 1.5 inch would resent too much of side effect. So ASTER limited the spacing to 1.5 inches, and hence the larger aggregate that can be considered is 1.5 inch. On the other hand, just staying in the States, the ASTM is currently working because they want to go beyond that. Say, hey, let's test whatever aggregate. No problem. The Resipod and variable geometries will be possible. You want to test 45 mm aggregate concrete, you have a larger spacing than that. And of course, you'll need to have a longer core. And let's see what the EN committees that are currently at work will put outside a standard. The point is that we, as PROCEQ, need to be able to provide a flexible solution in order to allow the user to perform all on-site and lab testing, surface and bulk. And the geometric kit is
suits everything,
coming from that.
Yeah.
Sure.
Fantastic. Thanks, Guido. So, on that note, let's just look at, just quickly look at how things actually work. The surface resistivity test is fairly simple because we got the current that's applied through the outer probes, and the potential difference is measured between the inner probes, as you can see over there. The current is carried out by the ions in the liquid, in the probe's liquid. So you need to make sure that's why your surface has to be wet. So does your probes have to be wet. And then the resistivity is calculated based on these probe spacing and the formula. It's fairly simple. What we actually have here for you is a little example, and we're going to show it during a demo. But we've taken the AASHTO recommendation for doing testing the cylinder for with the 30 for the surface test. The AASHTO recommendation is that you divide it in 90-degree spaced, and then do 2 sets of tests times 4. This is exactly what we're going to do for you right now during our little live demo session that we have. And Guido going to go ahead and perform this little test for us. So at the same time, you'll be able to see. For it? Yeah, go ahead. As you can see, he's got some water in there.
Of course, we just took our sample out of the moist room. So we're still in the lab, and according to the AASHTO, we marked the 4 lines that we'll be measuring along. So we'll start with the 0 line, and the device is pretty simple. It has 4 spring-loaded probes. So now it's easy, but even, and still going to answer some of the questions, it adapts even on irregular surfaces. What we see while measuring, is it readable?
Yes, that's perfect.
Okay, I need my pen.
Mm-hmm.
Okay, here we have a direct indication of the resistivity in kiloohm centimeter. As some question would involve what were the electrical parameters. Okay. This indicator tells us whether a 200 microampere or 50 microampere are driven through the outer probes, and the corresponding voltage is red in the inside probe. Okay, measurement stable. I will store it, and so on for all the required measurements. Now, the AASHTO is actually asking me for two measurements on each of the 4 lines. Mm-hmm. We'll stop sooner. And, well, we have something between 21 and 23 just to have an indication. And always with the highest current being pulsed through the outer electrodes. Say mean pulse because other question that arose. Yes, this is an alternated current, and it's a 40 hertz current that is driven. Mm-hmm. To answer the last question so far that I had, how deep does that go into the sample? Well, it depends on the spacing and on the resistivity. The broader the spacing and the higher the resistivity, the thicker will be the concrete that is interested by. As a rule of thumb, which we learn and we will see in the next session, we normally state that when testing on side, rebars are not so relevant after 3 centimeters of depth. Mm-hmm. So you can average that's more or less the order of magnitude that we're speaking about.
Sure. But next session, Guido, means Thursday. So now, thank you for the live demo. I personally find these live demos very, very useful, and it just you can get familiarized with the instrument a little bit better. Next,
I'm sorry, since we're just in the practical part and there is somebody asking for the option that we provide for foam tips instead of the metal ones that we have. Normally, we recommend using the standard ones, which may probably provide a quicker and more stable reading. They can even scratch the surface some. The foam tips are to be used whenever not on very insulating material, where not enough current is driven, then okay, go with the foam tips.
But as a rule of thumb, stick to the basic.
Yeah, that's a good starting point.
Fantastic. You just got to make sure that there's enough water in the pores of these probes. The next sort of procedure of carrying out is the bulk resistivity, where one thing to note here that before you start your bulk test, you need to compensate for the foams that you're going to be using, and these procedures are clearly shown in the manual of Resipod. But what you actually do, first step, you put the foams in, you make a measurement, and then you place a specimen. In this case, is a cylinder on top. The other thing to note, you need to make sure to set the instrument in the bulk mode using the software before you start testing, because your formula is going to be different. Provided you've done that, as you can see in here, you will have the resistivity then calculated, which is the area. K is the number of area divided by the length of your specimen, and times by the resistance of the actual concrete cylinder, and that will become your resistivity. And that's as simple as that. And the difference in this case is that we're looking at the resistivity of the entire specimen in comparison to the surface that we just shown you and done a little demo for you here. Let's have a look. Provided we've done the test for the surface or thing, then we need to kind of analyze the data. What numbers have we got there? It was 21 to 23. So what would you say that's, just give us a bit, like maybe if we were to analyze that, let your test be done over there. Analyze it for us in, let's say, a minute or so. Just going to break it down for us so we can understand it better.
Basic assumptions which are not true. We have to suppose that sample was just taken off the lime water or the moist room right away, and that here we have a temperature of between 20 and 25 degrees. Then we can assess that this sample would display a low penetration of chloride ion. It's somewhere in the middle, but when repeated on a statistically significant number of samples, we could classify that as a low penetration. Which actually brings us to a simple question that arose, that, well, effect of temperature. Of course, there is a strong effect of temperature, which is totally taken out of influence by the standard itself, because today we're in the lab so far and we are 20-25 degrees. Or each numerical value is referred to that temperature. We'll see on Thursday, when we'll be more on site, how to account for the temperature exactly. The general rule is the higher the temperature, the lower the resistivity. There are accepted.
We're going to break it down for you. We actually got some guidelines, some standards that we refer to as well. Today's that's the whole point of splitting up these sessions, but it's a good point you made. For those of you who have already registered for the Thursday session, it's all good, but for those of you who haven't now and have such questions, and these are the topics that you also want to kind of get to know about a little bit more, please go ahead and register for the Thursday session as well. There's going to be two sessions again, one in the morning, 9 o'clock Central European time, and one in the afternoon, 4 o'clock Central European time. Thank you, Guido. Now, on these bases, and this is again next session on Thursday, we'll break it down. Now that we know about resistivity a little bit more, one thing that I was interested to know was like, where can I actually, what on-site applications I would be able to look into with surface resistivity?
Absolutely. So we stated that we're on a new structure, and the main testing will be the lab testing. Yeah. But there are things that I can check and go out to the building that is being built next block. Basically, the strong dependency of the water content of the material makes the Resipod a very good tool for checking the homogeneity of the concrete, and especially in terms of its water to cement ratio. As I was telling you, especially in my country, the accident of having some additional water put in is quite likely to happen. Then this will have a deleterious effect on strength, but how can we check it today before it can display its final effect on strength? Well, electrical resistivity is the primary tool for checking water to cement ratio. Or another procedure that can greatly influence the final properties of the concrete, just like pouring, is the curing. We do fear, especially in the hot environment, a premature drying of the concrete, which could lead to cracking and defects. And then, once we have the structure done, checking different areas and assessing whether they are drying in a similar way, that is really a task that is at hand for the Resipod. I use this moment just to give some slight answer to somebody asking here, how does Resipod account for the effect of surface moisture when measuring resistivity? It does not. It is simply measuring it. So if we do have humidity standard, just like in the lab testing, then we can assess porosity and permeability. If it's not fixed, then moisture is what we're measuring, either because there is too much water in the concrete or because it is not drying properly. So there's no correction factor for moisture. No. It is something that is being measured. Last thing, which is still important here, which method is preferred, surface or bulk resistivity? Well, there are fans of both. Let's say that the geometry factor makes bulk resistivity more precise because there is a very simple shape factor. We drive current through the whole body of the sample and we measure it, no mistake. But no way of correlating that with an on-site measurement. So having a robust standard for the lab, for the surface resistivity test, allow us to have a strong data set to be confronted with when on-site testing. This is
fantastic. We'll get to all the questions in just a moment. Thanks, Guido. So we've got some examples here for when we actually can utilize. So just to kind of wrap up this section of the presentation, so is it like a systematic quality control procedure that we can have as we go through the processes of curing and curing a concrete?
New construction from the lab to the checking of the critical points of the on-site, the pouring and the curing
condition.
And of course, we still mentioned there the specific application, probably more popular in Europe than in the States, metallic fiber reinforced concrete with small fibers, steel fibers dispersed in the concrete. We want to check whether they reach a homogeneous distribution. Now, by measuring resistivity, we're not really measuring concrete resistivity in that specific case, but the fact that the conductivity is given by the steel fibers will actually allow us to assess by means of geometric different measurement to allow a homogeneous or inhomogeneous
of the distribution of these fibers.
Of these fibers.
Absolutely. Thank you. This session has been an exciting one for us. We've kind of gone over a little bit, but let's just quickly wrap it up, and we're going to start taking your questions. So, surface resistivity, like we had, it can greatly enhance the inspection flow. There are critical requirements for the construction industry to minimize the maintenance costs. And as we looked at it, you can see the benefits of this particular test principle by itself. We know now that electrical resistivity correlates very nicely with the existing test principles for durability of the concrete. So if you are able to utilize electrical resistivity test principle even more, that will greatly contribute to our performability and productivity. And on the other side, dependency of resistivity on the composition parameter of the concrete, it can allow it to be a very good quality control tool, and these techniques can actually help the course and the curing efficiency for us to analyze like we said, the pouring and the curing efficiency of our concrete for the new structures as we go through. And lastly, we looked at different scenarios, different applications, and there are several different kits and accessories available for you, different spacing for the probes. You got your bulk, like people are already asking about this. So all of these accessories and kits are available to you, allowing you to deal with several different specimens. So this almost minimizing the limitations where you can actually use such test principle. On that note, I would like to thank you for your participation in today's session. Now we're going to kind of start looking at the questions. If you want to ask your questions verbally, you can either put your hands up, because there's a little sign here to get raise your hand sign to get attention, or send a message to us via the Q&A box. But we're going to start right from the top. I got the questions here. I can see them, and we start going to deal with them one at a time. But at the same time, if you'd like to ask a question, please raise your hand, and we will be able to unmute your audio for you so you can ask questions. So let's start from the top.
Okay, we try to answer some of them just during the presentation. I'll start with a specific one that I apologize that wasn't clear enough about the use of the resistivity, of course, on side, on angular, on irregular surfaces. This is made possible by the spring-loaded device, and so I mean, any irregular surface will compensate for at least 10 millimeters of unevenness. This was actually an easy one.
I've got another question here. What are the electrical inputs used in the reservoir?
Yeah, we got that. And we mentioned that when measuring, we drive a 40 hertz alternated current, which, depending on the resistivity, can be up to a maximum of 200 microamperes.
Fantastic. Will we have access to the slides after the webinar? The webinar will be available in a recorded format, or you'll be able to watch it again from our YouTube channel. We should imagine it should be online within a day or so. So you will receive an email hopefully as soon as it's uploaded. Or you've got a American American standard that supports this type of inspection? We've covered that.
Yeah, I think there was a specific discussion about exposure classes in American standards. I don't have anything ready here, but I noted down that question because I might just have to provide some documents.
So we will provide such document. If you could please send us an email, and then we will look into that. We've got another question. Previous vendor type allowed different spacing between probes. The Resipod has fixed probe spacing. Why did you choose to fix? Again, we covered that. We have 38, 50, and you also got the geometric kit that allows you to provide custom spacing. So I think that question must have come when we were talking. When will the YouTube link be available? That should be available in, like I said, a couple of days or so. How exactly will temperature affect resistivity reading? Would resistivity measurement increase as the temperature increases?
It's the other way. Resistivity will decrease with an increasing temperature and will show the quantitative relationship on Thursday.
We show this in like a effect of it in a sort of percentage. What percentage value would have in the overall resistivity? Pardon. Okay, I'm just going to. There is an option for foam tips, which we covered that. How does Resipod account for the effect of surface moisture when measuring the ER?
We just touched that point before, but again, it doesn't correct or account for. It is what is measuring to. So you make it standard.
So we also have another question, which method we prefer surface or both? Again, is completely application dependent and what guidelines or standards you follow. When using Resipod in the field, how do you include the effect of reinforcing a steel? You need to locate your steel, i.e. use a rebar locator, and then draw it wherever and try to avoid them. Again, on Thursday's session, we will kind of cover all the different scenarios that you might be facing and what's the best sort of options you could choose.
There are some basic tips in order to minimize
the effect of the rebar.
It cannot be totally avoided.
Absolutely. Now, can we use a prism specimen 10 times 10 times 50 centimeters?
I don't think so. It is really too small for. I don't even think that. No,
that would be too small.
Too small.
Yeah.
We no problem with the standard cubes, 15 by 15 cylinders, of course, but below that, I'll check. But I would say that it's very too small.
I got a question about using the instrument for making proofs in the recent element of construction without considering testing in cylinders. I came from Bolivia, where environment conditions are totally different, where the ACI standards.
Okay, it doesn't mean that resistivity doesn't have a qualitative meaning, and what's most important, an aerial mapping of the surfaces. So there are references value for different type of concrete. We can provide that, and anyway, the criterion will always to define homogeneity. You cannot assess anything in terms of absolute thresholds in this case, but sure it will provide info about the building.
Are there some weather consideration for corrections?
Temperature. Basically temperature.
Which we covered. It is one of the main factors affecting the electrical resistivity. Okay. How does the initial field curing of sample affect the test results?
Dramatically. Dramatically. This is something that has to be taken into account. And in fact, just for mention the ASHTO standard, there is already a big difference whether the samples are just cured inside lime water or in a moist room. Just as a rule of thumb, the better the curing, the higher the final resistivity. So as long as we don't compare apples with pears, we can actually check whatever we want and bring the lab results on site. Mm-hmm. But of course, if the on site, you'll never get the same result on the same material if, as it is cured differently on lab or on site.
We got lots of questions. We need to go. I imagine that water cement ratio and cement time will also affect resistivity. So does that mean that the results are not comparable across sites, different mixtures?
Absolutely correct. Yeah. You cannot, but inside the same batch, you can find an anomaly and.
Absolutely. So you compare it apple to apple.
Absolutely.
We covered that earlier as well. Is there an ASTM standard for surface resistivity testing?
Not yet. Committees are at work for a surface resistivity with variable spacing and a bulk resistivity. Similar things are for European EN committee.
Okay. Sorry, the gentleman repeated this question. Whether the instrument shows relent results in
on an even structure. I apologize, I didn't answer that before. Yes, but with the springs that we have, we can accommodate a roughness of about 10 millimeters when measuring on site.
Fantastic. Now, if a lab sample has dried out, having not been cured according to the rest test method, do you have any experience attempting to resaturate the sample to the original condition? If so, how did you resaturate the sample?
Well, of course, you can put it in lime water or in the moist room, but it's not a matter of just allowing the water or the moisture in, because the curing condition is not something, it is different. It's not that you can pick up where you left when you let it. So you can reiterate it and measure it, but do not assimilate that behavior to what was cured properly.
Okay, thank you. Will the surface finish of sample affect the reading? This is a question that we came up earlier as well with the surface condition. Up to a certain degree of roughness should be okay.
Yeah, if we mean that, but of course, if we speak about layers. No, we cannot accept those.
Perhaps you could break down your question, Ray Chavez. Perhaps you could break down your questions and to tell us about if we're talking about carbonation, for example, on the surface, something along that line. So you need to break it down and tell us what sort of surface condition you're talking about. Then we can perhaps answer your question. In the event that the specified resistivity has not been met at the time of testing for new construction, what tools are available to project what the resistivity will be at some time in the future? What tools are available? Right. So basically, I believe the question is that if they haven't done the resistivity test to start up with,
and it's still unclear whether the test hasn't been done or didn't prove satisfactory.
In the event the specified resistivity has not been met at the time of testing for a new construction, what tools are available? Project what the resistivity will be at the time of future. Okay, so I think the question is here, if the numbers, when we did the resistivity test, and they didn't meet the guidelines and the standards, what if we wait for future and do the resistivity test? What would the numbers be affected at that place?
Okay. If you flunked the test in the lab, you flunked it.
Okay.
Because, that those values take already into account what will happen to them. So there is just like if you flunked a compression strength, measures have to be taken. I might just simply have to improve the protection of the concrete itself. I may use coatings, but no, there is no theoretical model that enables to project the evolution of resistivity.
Okay, thank you. What will be standard moisture state of the sample to be tested? We talked about moisture is obviously it has an effect on it, but there is.
Yeah.
You cannot define the actual amount of the moisture, can you?
No, but you can define the curing. So we standardize the moisture, just stating that the samples have to stay for a certain amount of time, just stated in the ash, so either in a lime water solution or in 100% moist room.
And then you're ready to do the test. Okay. Now, the resistivity, change in it. So it's just like concrete cover makes change the resistivity, which we covered that earlier as well.
Yeah, no, it will not, basically.
Is possible to make measurement on sample cube 15 centimeters?
Not a standard sample, but technically it's possible, and you can compare the results on the same samples.
Does the concrete cover is affected by the resistivity? So concrete cover affected by the resistivity, or resistivity is affected by the concrete cover?
No, it is not. The only fact related to cover is the fact that you might have some noise from the rebars, but you have to avoid those.
Okay. Is it also important the content of soluble salt as well as the pH, such as those taken into account?
It sure is. Its dependency is summarized in being composition dependent. Certain salts that might be used as additives will shift the resistivity to higher or lower values, so it has an effect, sure.
Do you expect to have a new design for Resipod? The Resipod is doing very well.
Not in the short time.
It's actually one of the instruments that I think has a very optimal design.
Absolutely.
And generally, this is a technical presentation. We don't touch on the kind of commercial side, even though that you guys, just for you had to do a special offer from our marketing side. But just to kind of cover now, the Resipod is actually fully waterproof. You can submerge it in water. It's IP67, and it's like I said, it's one of them instruments that it's pretty much does what it says on the tin. And we've had some great feedback from it. On-site institute, a lot of research centers, and that have been using it. Now, consider only the chloride ion should be considered. Only the chloride ion should be considered. I don't understand that question.
I apologize, Eric, I don't get it fully.
Eric Castillo, I've got your question. Consider only the chloride ion should be considered. Could you clarify that question for us again, and I will get back to you. And we got a question. How resistivity instrument works on fresh concrete?
It does not.
We covered that.
It does technically, but it really has no meaning.
Is there any difference between wet or dry specimen?
Absolutely.
Big time.
Big time.
You won't be able to test a dry specimen. You has to be wet.
Oh, yeah, well, actually,
the cores of the...
Sure. When lab testing, we need and we want fully saturated specimen. Of course, when we measure on site, we might recognize dry areas, and there will be the total different behavior.
Okay. What's the effect by the product, like fly ash,
microsilicon, they all increase the resistivity. The final resistivity of standard Portland cement will be lower than the silica fumes or ash concrete.
Now, the difference between, this is Professor Moody from Iran, the difference between lab and site results.
That while in a very short while a lab result can be used in a standard, or absolute thresholds can be seen and prescribed for lab testing, the same thing cannot be done for on-site testing. And so every specific on-site campaign, either as a backup of experimental data to compare the same material tested on lab, or we are under scenario 2. We know nothing about the structure, and then resistivity is only a tool for discriminating the different behavior of different areas. This is the it's a pretty broad question, and we'll try to answer.
Perhaps, Dr. Moody, you could send us an email in webinar@PROCEQ.com, and both myself and Guido will look into it.
Be happy to move on
but contribute together, perhaps.
If possible, we could update after the session 2 in order to which will be mainly on-site, and then have feedback and share our ideas on how to think.
So on that note, this session has gone for approximately 2 hours, I believe, and I'm going to ask one last time if there's any more questions. If not, I'd like to thank everyone for participating in this event. It's been very fruitful, and our expectations as well wasn't as to get this much interest. Now I've got another question here. Let's see. Does corrosion inhibitor calcium nitride in the concrete affect the resistivity reading?
Absolutely yes. And they will decrease resistivity specifically.
Great. So on that note, I think we're going to thank everyone. Again, thank you for participating. We will carry on doing such technical webinar. That is our goal at PROCEQ. And me and my colleagues, we're planning some great webinar sessions for rest of 2015, and for 2016 we're looking to come out with the proposal for webinars quite earlier in the year, and we'll again send all the information to you closer to the time when these webinars are due to be conducted. We would like to hear from you. So if you have any comments on a particular topic that you'd like us to cover, applications that you have, and some of your experiences with our instruments, again, please share it with us. Our email is at webinar@PROCEQ.com. And on that note, I'd like to thank all of you guys that participated, and also all my team at PROCEQ that supported us.
Thanks for our guest, Ali, for today.
Fantastic. Thank you. Bye-bye.